Bluetooth Low Energy has a great potential in embedded systems world, where you can have your smartphone, regardless of its brand, connected directly to your microcontroller to exchange data. Today in this tutorial, we have RYBG211 Bluetooth module from Reax connected to STM32 MCU configured as USB communication device class in order to build Bluetooth Low Energy to USB bridge application, allowing the exchange of data messages between smartphone and a personal computer. There are a lot to cover today, so stick around and let's jump on in. This video is sponsored by PCBWay. I've personally used their services to produce my own prototype for future IoT projects. Ordering your own PCB has never been easier before, with a lot of features like this castellated holes that I've used. Recently, they have upgraded their FR4TG standard to have even better quality with the same price. Alright, so here's my setup. As you can see here, I have my black pill board. It has STM32 F411 and it's connected over UART to this Bluetooth module from Reax, RYGB211. It supports 5.1 Bluetooth standard, Bluetooth Classic and Bluetooth Low Energy, of course. And my system will take its energy from the USB connector. I have this USB Type-C connected to my PC, and I have my STM32 configured as USB CDC. So when I plug this to the USB, my computer will see this system as virtual COM port. So let me plug this in. Yes. So now let me bring my phone to scan this device over Bluetooth Low Energy and see how it looks like. Alright, so now I have NRF application opened on my phone. You can download this from the Play Store. So here's my device, BLE bridge. As you can see, the RSI value is quite high because the distance is quite close right now. And this parameter is the BLE broadcasting period. It's set to be around 100 milliseconds. It's actually the default setting of the BLE module that we have here. This means that the BLE module is broadcasting every 100 milliseconds. So if we have a look at its details, we can see here the name. The device is low energy only, and it's discoverable. And here we have the unique universal ID of the BLE device. So now let's try to connect to this device. Yes, so now we are connected, and here we can see the characteristics. Alright, so from this characteristic, we can actually send data right away to our module, typing any value like 30 hex, and it will be sent. It's actually 0 in ASCII. So right now this packet has been transmitted over USB CDC to my PC. So now let me show you how the whole system works together and how the messaging between the smartphone and my computer can take place with the help of this module. Alright, so here I have QCOM application opened on my PC. It's nothing but a serial port communication application. So I have now my STM32 is connected to COM port 13. And no matter what the baud rate is selected, I can still communicate with it because the baud rate information will be included anyway inside the USB CDC packet. So this setting is not that important. Anyways, so now let me open the port and here on my phone, I have it connected right now. So let me enable the data reception on this characteristic. So now if I write anything, and then send the command, I can have it over here, transmitted. You can see here the data is sent in hex and displayed in ASCII as well. Hello from PC, just like the message sent from here. So I can send anything. You can see the message over here. So we can also do the other direction. We can transmit data from the smartphone to the PC over the virtual COM port. So I can write So yeah, let me think. I can send, let's send 3 bytes of data. Let's send, and you can see it over here, received to my PC. And of course, we can change the type of the message to be sent from my smartphone to a text message. We can write anything like hello world and send it. And you can see it received over here. So yeah, let me change the baud rate and show you that the baud rate information does not matter. Open again, and then I can send this message again, and you can see it shown over here. Today is Friday. No matter what the baud rate is, because we are connected over USB CDC. Also, I want to mention that this module supports long-range communication. I'm actually planning to do a long-range test in the upcoming tutorial, so stay tuned for that. Now it's time to jump into our code and see how to interface RYBG211 Bluetooth Low Energy module. Alright, so before discussing our firmware, let's have a look at the pin configuration of our MCU. So here I'm using Cube IDE development environment for STM32. And as you can see here, I'm using STM32F411. So yes, let's have a look at our peripherals. I want to focus on the USB part. First of all, in the USB on the go fast speed, the mode should be specified as device only because our MCU is going to be acting as a slave device. So this will do the job. And in the USB device, it should be specified to act as a communication device class, which is CDC, virtual COM port. So there's nothing actually to modify here. So let's move on. Of course, I am having only one UART port in order to interface my Bluetooth Low Energy module. As always, I'm having my DMA enabled for RX and TX lines. One thing I want to mention here is the clock configuration. Because I'm having the USB enabled, I'm not able to use the maximum speed of the system clock, which is 100 megahertz, so I'm stuck with 60 megahertz. Of course, this will be fine. We're not building something very critical here. So yeah, that's all regarding the pin configuration and the clock. Yeah, let's jump into our code and analyze our algorithm. Alright, so let's start with the main, where we have the peripherals initialization functions. And then we have the CDC handler initialization, where the USB interrupt handler is passed to it. So there's actually something important here to cover in the USB CDC handler function. We have here the handler is completely set to 0, and then we have the callback function pointer is assigned to this void function pointer. So whenever a data received over USB CDC, the past callback will be executed. And here we have pointers to the reception and transmission buffer assigned in order to point to the USB related buffers. Alright, so now let's see how things are going to take place in a real world example. So first let's have a look at the CDC initialization function of the USB full speed. Here we are having both the transmission and reception buffer that we have pointed at using the handler that I've initialized here. So I can access these buffers using these pointers. And in the USB reception interrupt subroutine, we have it over here, where we are receiving a buffer to the received data and the length of the received data. So here I'm passing the length of the received data to my handler, and here I'm using the function pointer that we were talking about. So with passing both the CDC reception buffer and the size of the received data, what's going to be executed actually is this function, the main USB RX task, where I am copying the received data over USB CDC to another handler and enabling the transmission over UART to send the received data to my BLE module. Of course, this part will be executed only if there is a smartphone connected to my module. Otherwise, a no connection message will be returned over a virtual COM port, indicating that there is no Bluetooth connection in order to transfer our message to. So when this flag is enabled, the received data over USB CDC will be put in the UART DMA buffer in order to be transmitted to the RYBG211 BLE module, so it can be sent over BLE to a smartphone. So far we have actually covered one way of data transmission from PC to phone. So now let's have a look at the other data transmission direction, which is going to be from the BLE module to the PC over the USB CDC. So here, as you can see, we have two tasks, the UART transmission and reception tasks that will be handling the interface of the BLE module. But first, let's talk about the AT commands that we are going to use in order to interface our BLE module. Alright, so let's have a look at the library that I have prepared to interface the BLE module. So here are the commands that I'm using right now. I've taken them from the document of the module. We have it over here. So let's talk about the important commands that I'm using. So here we have the broadcasting name of the device. As we have seen before, my device name was BLE Bridge. We can see it here from the main, where I am setting the name of the device at the beginning of my firmware. So the algorithm that I've implemented works as follows. The transmission buffer of the UART is passed to this function with the name of the device that I want to set. And then the AT command string is formed using sprintf function. And then the transmission flag is enabled. So in the transmission task, the prepared AT command is transmitted over UART to the BLE module. So now let's focus on the reception part. We have here the UART reception task. So in case of a received response from the BLE module, the received packet will be parsed first in order to determine what part has been received. So currently I'm parsing 3 packets that I'm interested in. I have the data packet and connection and disconnection packets. So from these packets, it's possible to know if there is a smartphone connected to the BLE module or not. Let me show you the syntax of these two commands. I have it over here in the module library. So in case of a new connection, I'm receiving this packet, and in a case of disconnection, I'm receiving this one. We can have a look at it from the module document right over here. So here we have the connection ID. After receiving this part, the MTU is received, its maximum transmission unit, which determines the maximum size of the packet transmitted over Bluetooth Low Energy. And in a case of disconnection, this packet is received carrying also the disconnected device ID. And in a case of a packet reception over Bluetooth Low Energy, the module will be notifying my MCU using the receive response, and we have it over here, which will carry both the connection ID and the string of the data received over Bluetooth Low Energy. So in my firmware, I have a dedicated micro for that, this one. So now let's follow the scenario of a received packet over Bluetooth Low Energy. Of course, this will take place in the UART reception task. And here in this function, the important data is extracted from the AT command, obtaining the size of the received data, and then the corresponding flag to enable transmission over USB CDC is enabled, which will allow actually the transfer of data to the computer side. We have it over here. So here the message that we have obtained over Bluetooth Low Energy is appended with feed line character. So every new message starts in a new line, and then the data is transmitted over USB CDC to the PC. Alright, so we have actually covered both data transmission directions. I have the code shared on my GitHub repository. You can have a look at it or even use it. And here I have the schematic of the system that we have designed, which allows Bluetooth to USB communication. So this brings me to the end of this video. If you have learned something new, please like the video, share it among your friends, and tell them about Useful Electronics. Stay tuned and bye bye.